Okay, let's take a look at these then. So what you do is we look, is it going to be zero order? And so we calculate the K for 1 and then the K for 2. So the K for segment 1 is going to be the final concentration minus the initial concentration over the final time minus the initial time. And so, look, 0.78 minus 1. Oh, actually, there's a negative here. And so it's what, 0.78 minus 1, 0.00. The time is going to be 25 minus 0. This is going to be molar per second here. And so what does that come out to? Can somebody punch that? 0.0088 molar per second. Okay, then we'll go on for the second segment there. And so we'll just plug in the numbers. For the second segment, the final concentration, 0.61, the initial 0.78, over the final time, which is 50, minus the initial time, which is 25. And so what does this? 0.0068 molar per second. And then what we're going to do is we're going to calculate the percent difference. You know, the best would be a percent difference of 0, that is, they have the same slope. And so to calculate the percent difference, what we're going to do is we're just going to take the biggest number minus the smallest, divided by the smallest, times 100%. And so what's the percent difference in those two? 68 and 88. 29.2%. So this doesn't look so promising. It looks like the slope is changing, right? Yeah. With each segment, so it doesn't look like it's zero order. So we'll go on to first order. For first order, we have to rearrange the integrated rate law. And when we rearrange it, we get K is equal to minus ln of A at time t over A at time 0 divided by T final minus T initial. In other words, the time segment that we're looking at. If you look at it, you know, this we call T, right? Or T, but it's the time segment. And so we just do this. We'll take the natural log. A at time final is 0.78 over 1 over the time segment, which is 25 minus 0.
What are you doing above? What are you doing above?
Take the natural log of 0.78.
I know, how do you end up with negative ln that over in final?
This comes from the integrated rate law. The
okay.
I just rearranged the integrated rate law.
Oh, yeah, thank you.
And so what does the number come out to? 0.0099. The units here are going to be in seconds to the minus 1. The units are different between zero order and first order because the rate laws are different. The rate is always going to be in concentration over time, you know, because the rate is just delta A over delta T. And so concentration change over time. And this is going to equal Ka, you know. For zero order, it's going to be Ka to the 0th power. So A to the 0th is just 1. And so K is going to have the units in molar per second, which means the rate is in molar per second here. Whereas in first order, the rate law looks a little different. It's going to be Ka to the first. And so the A to the first is going to be molar. And so K is going to be per second. So it's going to be molar per second, which is delta A concentration over delta T. So that works. Here. All right, this is for segment 1. We go to K for segment 2. This is going to be minus ln of 0.61 over 0.78 divided by 50 minus 25 seconds. 0.0098. seconds to the minus 1. And then we do the same thing. We calculate the percent difference here. So what is the percent difference? 1%.
So it might be first order.
It might be first order, but we should check because second order might give us, who knows, 0% difference, which might be better. We don't know because of noise.
But since our data is in absorbances, how can we convert it to concentration?
We use Beer's law to convert to concentration. Talk about that later. So that's first law. This is second law. I mean second order. For second order, we see that K is going to equal 1 over A at time t minus 1 over A at time 0 divided by t final minus t initial. This should be initial here, not the time. And so what you do is you use your invert key in your calculator. And so A final is going to be 0.78 minus A initial is 1. And then this is going to be 25 seconds here. This will be the time segment. And so you do 0.78 invert minus 1 divided by 25, and that gives you what? Okay, the units here are going to be molar to the minus 1, seconds to the minus 1. And that's because when we look at the rate law should equal delta A over delta T. Actually, I forgot to put the absolute value. Rates are always positive. You know, even if we're losing or gaining, they're always going to be positive. So that's going to equal Ka squared. So we have to square the molarity. And so the units we're going to get here, and you know, in the previous chapters, we ignored the units completely. In this chapter, we're going to go back and look at the units. You know, the previous chapter, why did we ignore the units in the previous chapters? Why was it okay to ignore the units in the equilibrium constant equation? It doesn't have units. Well, it does because it's molarity. No, it doesn't because it's not molarity. It's
Molarity over molarity.
no. I mean, you could have molarity over molarity squared. They don't always cancel. They don't always cancel. It's like, you know, if you look at the KSP, we're going to get molar cubed with PBI2. But somebody tell me, why is it okay to ignore the units there, but the answer is it's not molarity, it's activities. Activities are dimensionless, and we're just assuming that the molar concentration is close to the activity. So anyway, here we care about the unit. So this is going to be molar squared. So we need to cancel out one of those to get molar per second. Do that. All right, and then this is segment 1. For K for segment 2 is going to be 1 over 0.61 minus 1 over 0.78 over a time segment. This is the same as time segment 50 minus 25. So the units are going to be molar to minus 1, seconds to minus 1. And what does this come out to? .014 molar to the minus 1, seconds to the minus 1. And then we calculate the percent difference here, and we get what? 27%. 27% difference. So it looks like this should be a first order reaction. The first order reaction means that M is equal to 1. That's what we get from here. And then K, you know, the best K is just to average the two Ks. You know? We don't know which one's more accurate. And so we'll just take the average of the Ks. A. And in this case, we only have 2, so it's K1 plus K2 divided by 2, which is going to be about 98.5. 98.5 is going to round up to, you know, whatever. All right, from these we get the complete rate law. And that's usually what we're after, because with the rate law, we can predict things. And so, if we know the rate law, in this case the rate, which is going to equal, you know, the delta A over delta T, so the value, is going to equal K A to the first. Well, we know what K is. K is going to be 0.0095 molar to the minus, actually not molar, seconds to the minus 1, times A, concentration A to the first power, first order. And so what this allows us to do is predict the rate at any concentration. So if we start off with initial A of 1 molar, then that rate is going to be 0.098 molar per second. If we start off with a 2 molar initial rate, then it'd be double that. If we start off at half that, it'll be half that. So we can see the pattern and the slopes. When we see the pattern and the slopes, it's going to look like this. The curve is easy to recognize because the half-lives are equal, right? The half-lives are equal. And so the slope, you know, what we're looking at is the slope here. You know, gets cut in half with each half-life. So each time you cut the concentration in half, the slope gets cut in half. And so that's the way that this looks like. We can also take a look at the integrated rate law. So this allows us to predict the rate. Can predict the rate, i.e., you know, the slope at any concentration. Okay, the next thing we have is the integrated rate law. And so this is the rate law. Well, so, you know, questions like how long will something take? So for example, how long will it take to consume 95% of my, can I use the rate law to figure out how long it's going to take to consume 95%? So how long, let's say for 95% reaction. At 95% reaction, we have initial, or A at time 0, of whatever, just A at time 0. And then after this, we want an A final that's going to be 0.05 of my original. I only want 5% left over, right? And so I know my final and I know my initial. So can I calculate that based on this? So from here I could get my delta A. And so what I'm after is my delta T. How long does it take? And so can I use this equation? Delta A over delta T is equal to Ka to the first. Will this equation, can I solve it for delta T? This will be the concentration. No, I can't. The slope is always changing. Anyway, slope is always changing. If it were 0 order, I could just use the rate law. But since it's first order, I have to use the integrated rate law. So must use integrated rate law to answer how long and how much. The integrated rate law looks like this. And for us, we know what K is. You know, K is going to be 0.00985.